Okay, in system of conservation laws, we want to construct the interface flux. So let's say we have Wi here and Wi plus 1 here. Both are vectors, so both have multiple variables. We need to construct the interface flux. With this discontinuity, it is in general very complex to solve the Riemann problem. Okay, because you have many different cases. Think of just the case where you have two variables. These two variables can take a lot of different combinations. You basically have you basically have a four-dimensional space to explore, right? So you have two variables on each side. There are four different numbers you have to consider in order to solve this Riemann problem. And if you have a three-dimensional, four-dimensional, five-dimensional system, you're looking at a three-dimensional space. It's very complicated. There are special cases you can work out, like for Euler equation. You can work out some special cases, but in general, it's very hard. So, in most cases, we resort to this approximate Riemann solvers. And today I'm going to introduce a particular approximate Riemann solver that again is going to give you an entropy satisfying solution, but that is more dissipative or less accurate than as if you can exactly solve the Riemann problem, like the Goodenough scheme in the scalar case. This is called a numerical dissipation. Okay, the idea is the idea is from the fact that an entropy satisfying solution is the extreme case of a solution to a viscous differential equation, or differential equation with dissipation, as the dissipation goes to 0. So the idea is, when we are solving this equation, why don't we add some numerical dissipation to the system? And the numerical dissipation acts like a physical dissipation, but without taking the limit of 0 dissipation. So with finite dissipation, it is approximating a physical solution with some dissipation. And as the numerical dissipation goes to 0, which is by construction the case when the grid refines to a very fine grid, then I would converge to the physical entropy satisfying solution. All right, so this is the numerical dissipation is like the following. I'm going to construct my flux, which is a function of Wi and Wi plus 1, and in the reconstruction case is WL and W right. I'm going to approximate this as the average of Fi and Fi plus 1, which I think we tested out the first day we discussed finite volume is unstable, right? Things just gets wildly oscillatory. But then I'm going to add a numerical dissipation. I'm going to add a numerical dissipation I call D times the half of Wi bar minus Wi plus 1 bar. Okay, and I'm going to construct D such that it is D is let me see if that is right. I'm going to construct D such that in the linear case, so if I have D is such that for F equal to constant times, let me say F is equal to a big U times W, we get upwinding. Okay, so let's analyze exactly what D we need. So if F equal to a big U times W, the big U can be positive or negative depending on which direction the wind comes from, right? So that means we have my F of I plus half would be equal to a big U times Wi plus Wi plus 1 over 2 plus this D times Wi minus Wi plus 1. So let's say if U is positive, which direction is upwinding direction? Left, and should I take Wi or Wi minus 1? I should take Wi, right? So if U is greater than 0, my F of I plus half should be equal to Wi. And what value of D do I need to make this equal to Wi? Just U, exactly. And if U is less than 0, should I take Wi or Wi plus 1? Wi plus 1, and what value of D do I need? Minus U. So either case, D is equal to absolute value of U, or the magnitude of the speed of the wind, right? Or if I add enough numerical dissipation, this is numerical dissipation, where the dissipation is equal to the maximum wind speed, then I get upwinding behavior. This generalizes to the case where F is not just equal to U times omega. This actually generalizes to the full case where F depends on W in a very complex way, but as long as we can compute the Jacobian of F with respect to W, we know the various eigenvalues of this Jacobi, which gives us how fast various wind is blowing towards different directions. And we know as long as we take D to be large enough so that it is as large as the magnitude of the fastest characteristic, we are going to be fine. We have enough numerical dissipation to upwind all the characteristics. What is this U? This U is a special case where the derivative of F to W is equal to U. In general, let me insert another slide. Show from current slide. Yeah, in general, so we have this U. If partial F partial W is equal to a matrix, then I can let D to be the maximum of the absolute value of the eigenvalue of A. That gives me enough viscosity to construct the FUI. Let me write WI and WI plus 1 to be half of FWI plus F of WI plus 1 plus D times half of WI minus WI plus 1. Okay, this is the interesting term here. This term is approximately equal, as you can see, is approximately equal to minus D times partial W partial X times delta X, right? Oh, actually, I have a half here. It's a times, yeah, let me just write as half of delta x. So it is like adding a viscosity into the flux. It is like adding a viscosity term into the flux that is proportional to adding a viscosity proportional to half of delta x times d, where d is the max eigenvalue of the Jacobian. So the magnitude of d is fixed no matter how you refine the grid, right? It is just equal to something relating only to the differential equation. It doesn't relate to the grid. But as you refine the grid, half of delta x would go to 0. So the amount of dissipation you add into the system, the amount of artificial dissipation or numerical dissipation or numerical viscosity or artificial viscosity, I mean, that's different ways people call it, is going to go to 0 as you make delta x go to 0. Okay, that's how numerical viscosity works for system of conservation laws. It is a way to approximately solve the Riemann problem, which gives you interface flux in the presence of discontinuity. Any questions on this?